Hello. I will be going over the Euclid 2021 question 9. So to begin, um, looking at this question, let's just read it over. Suppose that A is equal to 5 and B is equal to 4. Determine all pairs of integers KL for which K squared plus 3L squared equals to A squared minus AB. Now, this problem is pretty straightforward. In the beginning, we just substitute A and B into the values of K respectively. So let me pick a color here. Oh, that's a bit too thick. Um, so K squared plus 3L squared would equal to 25 plus 20 minus A times B. Sorry, this will be 16 minus A times B, which is 20. And then let me pull out my calculator here so I don't mess up the simple addition. So this value would give us 25 plus 16 minus 20 will equal to 21. So K squared plus 3L squared equals to 21. Now, at this point, how do we approach this problem? Well, I'm just going to move L squared, this term here, to the other side. And this would be K squared equals to 21 minus 3L squared. And then we factor out the 3 from the negative 3 from the right-hand side. And this would equal to negative 3L squared minus 7. Now, at this point, we have to notice something clear. This side is positive, right? Because K squared is positive, any number squared is positive. That means this side right here must also be positive, right? So if we want, sorry, if we want this side to be positive, then we want both these terms to be negative, right? We want, because this term is less than 0, that means this term is also less than 0. So we could put a bound on L basically. So we say L squared minus 7 is going to be less than 0. So L squared is going to be less than 7. So let's say the absolute value of L is less than the square root of 7. And we notice that the square root of 7 is around 2.6. So we say the absolute value of L is less than 2.6. And we also notice something else. We notice that for every value of L, negative L also satisfies the equation. Why? Because we look at our equation here, right? Everything is squared, right? So if we just take negative L, we square it, it's going to be positive. It's the same as L squared, right? So now that we have this in mind, we know that the absolute value of L is less than 2.6, and we also know that for every value of L, negative L also works. So let's work with that. Interesting. My eraser's not working. My eraser isn't working. Okay, there it is. So I'm going to leave this here. So the absolute value of L is less than 2.6, and L works, then negative L also works, right? So let's just brute force this problem. So let's just suppose that L equals to 0, right? So if L equals to 0, then K squared would equal to 21, right? Then this has no integer solutions, so this doesn't work. Now let's say L equals to 1, then K squared plus 1 would equal to 21, then K squared would equal to, or sorry, it would be K squared plus 3L squared equals to 21. Then this means that K squared would equal to 18. This doesn't work. This has no integer solutions, right? Now, let's just say that L equals to 2. Then it'll be K squared plus 3 times 2 squared would equal to 21. And then K squared would equal to 3 times 4, which is 21 minus 12. K squared would equal to 9, and this does have integer solutions. K would equal to plus or minus 3. So because we know that it works for positive 2, we also know that L could equal to negative 2 as well. So in the end, our answer is um, LK would equal to plus or minus 2, comma, plus or minus 3, like so. Now moving on to problem B. Um, Prove that for all integers KL, there's at least one pair of integers AB for which k squared plus 3L squared equals to A squared plus B squared minus AB. So we have integers K and L, right? So they exist. We know that they are numbers. And we want to prove that for every value of K and L, there's going to be a value of A and B that satisfies this equation. So how do we approach this? Well, I'm going to look at this right here, and I'm going to make this a little clear for you guys. A squared minus AB plus AB plus... What does this look like to you? If you look at this kind of looks like a quadratic, right? Because we have our quote unquote x squared terms, and we have our bx term, and then we have our constant values, right? So whenever you see these type of questions where they have a quadratic or like a hidden quadratic, you just want to apply the quadratic formula. I noticed that it works a lot of the times. So let's just rearrange this to make this a little bit more clear. Minus 3L squared plus k squared minus b squared, like so. And then in our quadratic formula, this would equal to our f squared, this would be our bx, and this would be our c. And we just want to substitute it into a quadratic formula, and then hopefully something happens, right? Something magical happens. So let's just take a would equal to negative b, or negative b, which would be positive b, plus or minus the square root of b squared minus 4ac. So I'm just going to write positive 4 times 3L squared plus k squared minus b squared, like so. All of that over 2. A would equal to b plus or minus the square root of b squared plus 12L squared plus 4k squared minus um minus should be 4b squared, all of that over 2. I'm just gonna move this up so I have some space. Okay, that didn't work. Okay, that worked. And then at this point, we can simplify this a bit, just simplify it inside of roots, plus or minus the square root of negative 12L squared plus 4k squared minus 3b squared, all of that over 2. And actually, I'm going to do something here. I'm going to rewrite this. I'm going to rewrite this a little more clearly. 4k squared plus 12L squared minus 4b squared. Now, we want to find B in terms of L, basically. We want to say B would equal to something something involving L, right? And then what we also want here is we want this square root to cancel out with something, right? So we have to observe something here. We have to observe something on our own here, and that is that if, hold on. Oh, sorry, this should be a 3. This should be a 3. We want to observe something here, and that is that if we try and make these terms 0, then this whole thing will cancel out because the square root will cancel out with this because this is a perfect square, right? If you take the square root of this, it's going to be 2k, right? So we want to make this equal to 0 somehow, or it's like just remove it or complete the square, do something with it, right? So we have to observe that if we let b equal to 2l, then something magical happens. And that is that a would equal to b plus or minus the square root of 4k squared plus 12L squared minus 3 times 2L squared all over 2. And then we notice that a would equal to negative b plus, or sorry, positive b plus or minus the square root of 4k squared plus 12L squared minus 12L squared. And then this kind of makes our L's cancel out, and we have a value for b for every L, right? So a would equal to b plus or minus the square root of 4k squared over 2. And then a would equal to b plus or minus 2k over 2. And we just substitute our b value here into here. And then this would equal to a would equal to 2l plus or minus 2k over 2. And a would equal to l plus or minus k over 2. Or sorry, plus or minus k. And just to make sure, let's just substitute it back in the equation to make sure that it actually works. I'll do that in a second right here, once I create some space. So b equals to 2l, and then a would equal to l plus or minus k. And if we do that, then we see something cool happen. So let's just say our left-hand side would equal to k squared plus 3l squared. Our right-hand side would equal to a squared plus b squared minus ab. And if we just substitute it back in, like let's say we substitute l plus k in this case. So let's just say l plus k squared plus 2l squared minus l plus k times 2l. This would equal to l squared plus 2lk plus k squared plus 4k squared minus 2l squared minus 2lk. This term and this term cancel out. And then in the end, what we're left with is interesting. I think I messed up somewhere. Minus 2l squared. No, 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 I didn't. Okay, so in the end, this would equal to, we collect, should be a L. We collect these terms together. So it'll be L squared plus 4L squared minus 2L squared. So this would equal to 3L squared. And we just have a K squared here. So left side equals to right side. Therefore, b equals to 2l, and then a could equal to l plus k. And you can actually verify with l minus k, it also works. So you could say a is equal to l plus k or l minus k. I'll leave that to check for yourself. It honestly doesn't matter because you just have to prove that there is at least one pair of integers, right? It doesn't matter if it's l plus k, l minus k, it's all the same. So what this basically means that for every value of a, or sorry, for every value of k and l, you could select b to equal to double of l, and you could select a to be the sum or difference of the two l and k. Now I'm actually going to keep this here because we're going to need this for later. This is very important for part C, actually. And we also have to make another observation for part C, and that is that it's this equation almost has a certain level of symmetry to it, right? Because we have a squared, we have one a squared, we have one b squared, and we minus a and we minus a b, right? So it doesn't matter if a is the first term. Like for example, let me make this clear. AB would equal to b comma a, right? Because they both have the same effect on the right side of the equation. It doesn't really matter. We can abuse this symmetry later on, and I'll show you how. So prove that for all integers a and b, there's at least one pair of integer kl for which k squared plus 3l squared equals to a squared plus b squared minus ab. So we're given integers a and b, and we want to prove that there is a value of L and there's a value of k, right? So let's say b is even. Well, looking at this, we could just say that b over 2 would equal to L, and L would still be an integer, right? Because b is even. So case 1. B is even. So let's just say b over 2 would equal to L. And let's just substitute this back. So, and then we say that, let's say, a would equal to L plus k. So therefore, a minus L would equal to k. And therefore, a minus b over 2 would equal to k. Just substituting that here. And then, so these are our two values. right? So let's just substitute it back into our equation. So on the left-hand side, we have k squared plus 3l squared. This would equal to a minus b over 2 squared plus 3 times b over 2 squared. This would equal to a squared minus ab plus b squared over 4 plus 3b squared over 4. And then if we add these two terms together, we get equal to a squared minus ab plus 4b squared over 4, which equals to a squared minus ab plus b squared. And this equals to our right side, right? So our case one is that if b is even, then we could select b over 2 to equal to L, and then we could select a minus b over 2 to equal to k, right? Now, what happens if a is even and b is odd? Or sorry, what happens if a is even, right? It doesn't matter what happens to the a, or sorry, the other number, right? So what happens if a is even? Well, remember what I mentioned about symmetry? Well, we can actually abuse that symmetry here because we could just change a, b to be equal to b, comma, a. So we could just select a over 2 to equal to L, and then we just do the same process again. And then we just say b, or sorry, we just say k would equal to b minus a over 2. And then we do a similar process again. And then if we simplify and expand this by substituting into this equation here, right here, we notice that it actually does equal to the right-hand side, right? Because they are interchangeable. It doesn't matter if A or B, what order they come in. Now, I talked about if B or A is even, but what if neither of them are even? Well, we can't do the same trick anymore, right? Because if we do A over 2 or B over 2, it won't give us an integer, right? And we want only integer solutions in this case. So what do we have to do? Well, to be quite honest, I have no idea. I kind of just guessed on contest and just got it right. So what we have to observe is that we can let L, or sorry, let's say we can let A equals to L plus K, and we can let B equal to L minus K over 2. Because what this does is because they're both odd numbers, if we add them together, we get an even number and we divide it by 2. And then if we subtract them, we also get an even number and we divide it by 2, and then we have integers. So if A and, or sorry, I think I did it the wrong way around. Hold on. For all integers A and B, there is at least one pair of integer K and L such that, okay. If A and B are both odd, well, we can just select L to be equal to A plus B over 2, and then K to be A minus B over 2. And then what we see happen here is if we substitute it again, once again, um, we notice something very special happens, and that it actually simplifies into what we want. And just give me a second. Let me think about this. See if it's actually correct. Yes. Okay. Um, so let's just check again to see if it actually works. So we say a squared. Okay. We say our left-hand side would equal to k squared plus 3l squared. And this would equal to a squared minus 2ab plus b squared all over 2. And then our right hand, and then it'll be 3l squared plus 3 times a squared plus 2ab plus b squared all over 2. And then we could just add these together. Sorry, I think it's a 4 here actually. Yeah, it's a 4. So these are actually both 4. And we could just add these two terms together. So it'll be 4a squared um plus 4ab plus 4b squared all over 4. And this would equal to a squared plus ab plus b squared. And that concludes our proof, right? So for every value of a and b, you can always select L to be equal to a plus b over 2 and k to be a minus b over 2. And you might be asking, well, how do I come up with these values, right? How did I come up with this? Well, honestly, I just guessed. When you do enough problems, you start to notice patterns that just come out of nowhere. Seemingly, it becomes intuitive, and you just kind of do more and more practice problems, and eventually, just kind of be able to guess kind of these solutions, basically. And yeah, that is question 9 of Euclid 2021.